Thank you very much. It's really exciting to be here and walking the exhibit halls downstairs and seeing the technology and what you all do is just incredible. Let's see. So you already heard this from the person just prior to me, but I did start 128 Technology. I was one of the founders. And 128 Technology is a software-based routing company based in Boston, Massachusetts. And we wanted to set out on a bold initiative to be really innovative and try to fix networking by just rethinking it from the ground up. And if you think about networking, it's really the way it operates today, where we use IP address ranges and we advertise routes, and we combine those routes when we can to be efficient. And we have to do it in two directions to create an anywhere-to-anywhere network of connectivity. And that's just great. It works. We just have to have a uniform address space, despite the fact that our private networks don't share routing policies or network intent with our public networks, of which we have two that don't talk to each other either. And the fact that almost every use of the network today goes across more than one of these types of networks. It usually starts in a private network and usually ends in a private network with one or two public networks between them. And our networking routes and our advertisements and our network intents don't cross borders. It makes it really challenging. And so we set out to say, well, how could we fix that? And I don't know how many of you have used Gmail. I suppose everyone uses Gmail, but the web client. And you know, it's truly an astounding piece of software from a networking perspective if you think about it. You could be sitting there at your house or at your office and typing in a draft of an email. You haven't sent it yet, and every character you type in goes into that application somewhere, wherever it is. And just be mindful of the hundreds of millions of people doing the same thing that you're doing. And then you close your laptop and go to Starbucks, and while you're in line, you open up your phone, and you can begin typing the very next character into your phone. I mean, you're on a different IP address, different network, different device, and they're able to, from a user session service capability, make all that network stuff invisible. And how do they do that? How do these applications do it? They do it with what I'll call a cookie or a piece of metadata, a piece of information that is transmitted, that reconnects you with your authenticated being of who you are, and in the case of this Gmail application, reconnects you with exactly where you are, the exact state, securely, exactly where you were in typing that message in. And it's just, when you think of the scale of what they do, it's absolutely incredible. I mean, and we look at how complex our networks are, and you say to yourself, there has to be a better way. So that's why we started 128. We wanted to figure out a better way. Prior to 128, I started a company called Acme Packet, and I was the founder of that company as well, and we made session border controllers. And most of you know that voice over IP is probably one of the hardest applications to run consistently well over multiple IP networks. And session border controllers help make voice over IP work across network borders. And we learned, for 13 years, we learned every network problem under the sun that had to be solved and fixed. It was a perfect laboratory to prepare me and my fellow co-founders for starting 128 Technology. Juniper Networks completed the acquisition of our company, 128, last December, and I could not be more excited about being part of Juniper. Not only are they probably the leading networking company in the world to understand the true power of AI and ML as it applies to running networks, they've really embraced our secure vector routing technology, which I'm going to share with you today. Oops, pushed the wrong button. So these next 4 slides that I'm going to talk about are talking really about the changing shape of the internet and how things have changed. You're all very, very smart people, so I'm going to zoom through these really fast. But we went from networks that were leased line connected or private line connected in the beginning of the internet, where most of the data stayed on site, and the killer apps were email and file servers exchanging files. And as the network evolved, companies started to connect these pre-existing networks to the internet, Once again, primarily for the purpose of email, but also for accessing information. There was some information access. And of course, as the next decade rolled on, carriers, service providers started providing all kinds of WAN-based services, and the amount of data that was staying on site was reduced, and there was more and more internet activity. And then finally, in 2020, basically everything is in the internet. All the services are in the cloud, and we're still based on carrier-based SD-WAN type services. The new thing is SD-WAN. And now, there's less and less or zero data on site, maybe 20% in the headquarters, but the bulk of what we're doing today is moving towards the cloud. And so this is really like the network is changing shape, and it's been evolving continually. And SD-WAN, which I'm going to talk about here today, the original definition was all about separating control from, separating the data plane from the control plane, and things like open flow and all this nonsense that people were talking about 6, 7 years ago. But in reality, what SD-WAN is today is something called multipath routing. It's probably something that, if you think back, routers should have been able to do a long time ago. Why can't routers have multiple pathways and route traffic intelligently on them? That's a very good question to ask. I asked myself why it took so long. The other two basic capabilities necessary for people that want to run an SD-WAN network are zero-touch provisioning, and that's just a requirement for everything in today's network. We need that stupid, simple capability that everything just works. And of course, a way to, people call it a single pane of glass to control it all, one place to manage, see, visualize, and operate the network. I'm just going to quickly teach a little bit about what multipath routing is. And I have a few slides on the capabilities of what SD-WAN, the SD-WAN marketplace generally supports. And obviously with multipath routing, you want to use any pathway that you can between a site and, in this case, the headquarters. It could be any path through any set of different networks. Classically, people use MPLS for security and for performance reasons. But frequently, it's expensive, and they want to use DSL, cable, or fiber. There's also, you can add satellite, and you can add just about any other kind of transport you can think into this model. What the SD-WAN products do, including Juniper's SSR, is they actually measure all these pathways in real time. They're always monitoring them. They're trying to figure out which ones work, which ones are having packet loss, what is the actual capable performance of a pathway in terms of throughput, bandwidth, what's the jitter, the latency, and the packet loss. And then they take all that data and information and they start using it to make smart choices about where to route traffic, which application or which kind of traffic should go on which interface and why. And in your line of work, you may have security requirements that I didn't list here in terms of which network you pick for which type of traffic. And some of the folks in the SD-WAN business actually spray the packets across multiple interfaces for a single network transmission or a single file transfer. They'll actually spray the packets across multiple interfaces. There's an advantage to that is you can move a larger file faster. The disadvantage is that you have to build a jitter buffer on the far end to sort of reassemble those packets. And that tends to take about 80 to 100 milliseconds, and that's a little bit of an expensive latency hit, but some people do that. One of the things that most of the vendors have today in this space across these pathways is forward error correction. Forward error correction is useful if it's a microwave link or if it's a link that has consistent packet loss. It's not really that useful otherwise, and it can consume a lot of bandwidth. So most of the SD-WAN solutions today turn it on or turn it off or have a configuration knob to say use it or don't use it. Also, TCP acceleration for satellite use or long latency. Anytime the latency gets high, the SD-WAN solution should, and the Juniper SSR does, automatically turn on TCP acceleration to make sure that the latency is not impacting the outstanding packets across the wire. And this is something that the Juniper SSR has that no one else has, which is a conditional encryption. If something's already encrypted, why would we want to waste the horsepower to encrypt it a second time and also potentially introduce extra packet fragmentation? All SD-WANs on the planet except the Juniper SSR use a tunnel for transport. Typically they use IPsec tunnels, and typically they have GRE headers in them. Take, for example, VMware has a VeloCloud. It has 130 bytes per packet that they put on the front of every single packet in the network. And you might, and people will say, yeah, but it's a 1,500 byte packet. The percent overhead isn't really that great. And at first, we thought that was true. And then we started looking at real customer situations. And it turns out this 130 bytes actually adds a lot of extra overhead, as much as 30 to 40% on a typical corporation network. You see, your applications have changed. When you are typing into Gmail, or you're using Office 365, or you're using, pick the new application you're using, every keystroke you type goes across the wire, every single one. Those packets aren't very big. Every voice over IP packet, 80 bytes, not very big. There's a lot of small packets. And even if you're sending the maximum size packet, the TCP ACK that comes back is a very small packet. So in actuality, we've noticed by actually measuring real customer networks, like we implemented our solution at a pharmacy chain, and they have a 37% bandwidth savings because of not using IPsec tunnels and going with a tunnelless approach that we have. And that 37%, at first they said, well, it doesn't matter. We have so much bandwidth that doesn't matter. But what it really meant was 37% less security stacks, 37% less head-end routers, 37% less stuff to worry about. And it actually does have a huge savings. This is a giant waste, and it adds no value. Tunnels are used to get packets to go where they wouldn't go otherwise. That's it. I mean, you can do encryption without a tunnel. If you could get a packet to go somewhere without using a tunnel, that's what we do. And I'm going to share with you how we do it. So our tunnel-free approach, and I'm going to go into a little more detail in the next slide, actually does what that Google application does. We look at the new packet that's being routed, and we know it's part of an application layer session, and we actually put the network intent right in the first packet. We don't send an extra packet, we stick it right in that first packet. Typically it's a SYN packet, there's plenty of room. And in that metadata that we put in that packet, we identify everything we need to about this particular session or service that is being routed. All the network intent, we identify what we call the tenant, which is a text name for where this is coming from. We have a service, which is a text name, which is where it's going to. And having these text names solves the problem of, well, what about addresses and private addresses and public addresses? These text names have meaning across the entire end-to-end network that we're trying to build. And then the subsequent packets actually don't need to include any of that information. And they're actually natted. I'll show you how on the next slide. They're actually natted essentially like IPv6 segment routing is. They're sent right to the next hop router's interface. The destination address is the source router's interface, and the destination address is the destination router's interface, and the port numbers are assigned or made up by the source of the session to make them unique. So every single session has a unique 5-tuple on the wire. This is a more detailed example of how it works. When a new session comes in, first packet's identified, and just like all routers, it's got that today in the network that we all use, they have a first packet processing routine. They call it a slow path. And then once they figure out where the packet's going, they add an entry in a flow table. And all subsequent packets are routed the same way, unless the flow tables, unless the entry falls out of the flow table due to timeout or the flow table fills up. There won't be more routing done. It will simply use the results from the previous routing of that first packet. So we do the same thing, and we detect that new session, and we look up where the packet, we figure out where is this packet going, we identify the type of services or sessions or routes that we figure out where it's coming from, and that's step 2. And step 3, we insert that metadata cookie into that first packet, just like your Gmail does when you connect to the network. identifies everything we know about that packet. The tenant, where it's coming from, its source address, original destination address. We also insert something that we call like a session identifier. And the nice thing about the session identifier is it gives you something to track end to end. Once all that metadata is assembled, it is encrypted and it is signed by the first router for the second router. These two routers have a security association that pre-existed this packet being transmitted, which allows a very secure way for us to send metadata and what I consider network intent between the two routers. Then we nap the packet to have the addresses. You can see it in the diagram. It's called waypoint 1 or WP1, sitting right next to that left SSR logo or circle. And on the right, there's another one called waypoint 2. We use waypoints because we think of them like air traffic control when you're really going from router to router to router. If you study IPv6 segment routing, you could think of it as a segment ID. But by routing between the interfaces, by the way, these addresses are already there. It requires no new allocation of any IP address. Every router has IP addresses on them, and they don't use them other than to ping them. They're not really used. In this case, these packets are using the addresses on the wire. And they can actually pick not only the next hop router, but the specific interface on the next hop router, allowing all kinds of very interesting capabilities around load balancing and around essentially doing what lags do, but just as a natural part of routing. And so in the end, it gets to the destination router. The metadata is there. The destination router decrypts the metadata, restores the packets to its original addresses, removes the metadata from the first packet, and statefully remembers this flow or this session for any subsequent packets that might be coming along. And both sides do the same thing, and so now we've done this work one time on the first packet, and we've essentially completely routed the session between these two routers, including the return path. So that's what makes it a vector, is that I have a route from me to you, and I can automatically enable the return path. I don't need separate routes to open up to get the path, to enable the return path. All that these routers need is to be able to talk to each other. So this creates what we call a zero trust WAN, a WAN where every single session is uniquely sort of containerized in a way from each other. And our objectives in our zero trust setup is to have directionality. I mean, these are the controls you need. You need to be able to say, I can talk to that service, you can't, and that service can't talk to me. You need to be able to segment things, and segmentation is cryptographical, or we have to separate every kind of use of that network one from another using different cryptographic keys potentially, or find ways to make sure that there's no packets that can leak across any of these segmentations that we have. And you need very granular policies. On verification, we have to have continuous validation, and what I mean by that is every single packet has to be signed between these two routers. You can't allow any replays attack, and that signature has to include some notion of the current time, so that you can't sort of record packets on the wire and then 10 minutes later replay them. You know, so that none of this metadata is dangerous in the sense that it's a key that opens the door. So we have to be certain, absolutely certain, that it is signed with a time-based HMAC key. And also for transparency, because we're routing individual services and sessions, we have tremendous amounts of notion of what's going on, real-time analytics about what users and what tenants and what services are using the network for. To achieve what we've done with today's equipment, you would have to deploy all kinds of routers to create your anywhere-to-anywhere network. Then you would need to deploy all kinds of extended ACLs to create your one-direction connections or communications. And then you would actually have to build all kinds of overlay analytics capabilities to grab all the metadata from these network connections to get the information on the right that you need to secure and control and manage the network. So we call it microsegmentation and zero trust. Every single TCP or UDP session between these two networks is in its own container. Its packets are encrypted. They're completely separated. They have a unique and hard to understand sort of profile as they go through between these two green routers. Their IP addresses are only the addresses that are on the router. There's no connection with what services they are part of if you were to listen in or eavesdrop in the middle. Each of these different colored segments can have different cryptographic keys in the middle, and connect to VLANs or whatever's on the left and right sides of these routers, creating this microsegmentation and zero trust model. And these are directional models. If you look at these arrows here, we used a retail example. If you look at these arrows here, you can see that they show directions, and they're not all the same. So, for example, the sales database looks like the store can talk to the data center, but the data center can't talk to the store. And it doesn't mean there isn't bidirectional packets flowing. It's like a phone call. I call you, and there's audio going back and forth in both directions, but you may not be able to call me. And that's what firewalls do. They create notions around who can talk to who, and that's all part of the secure vector route. And you have to wonder why routes never included who can use them. Like, why didn't they? I mean, if they did, you would have secure vector routing. And you'll also notice there are some routes that are bidirectional, like the telephone. It looks like, the arrows go both directions between the PBX and the phones. And so you can have policies that allow routes to be bidirectional or unidirectional, from left to right or right to left. And this gives you all the controls you need, along with the microsegmentation. More things that you might need. You obviously need a bunch of certifications. We don't have all the ones that the folks in this room want. We're working on it. I think we're involved with going through the JITC testing process. But you got to have basic FIPS 140. You got to go through all these different tests and capabilities. We also, our deny by default policies, basically when you configure our router and don't have any routes in it, it won't route anything anywhere. And you have to actually decide what services you want to route where. And that's deny by default, means you don't have to worry about creating an anywhere to anywhere network and then add ACLs on top of it. These come for free. Every router to router communication is authenticated on every packet, every single packet. And the ability to do adaptive encryption is actually really important to make things scale, make things easier to use, make things have lower latency. Encrypting things that are already encrypted isn't adding a lot of value, and as much as 80 or 90% of what is going across WANs today is already encrypted. And so the question you have to say is, why isn't it 100%? And the things that aren't encrypted tend to be things like NTP, DNS, and maybe they should be encrypted, but they're not encrypted. But any kind of modern service, even Netflix, everything's encrypted today. And so you're not really gaining much by re-encrypting it. You're using a lot of extra horsepower to do so. And when you have a tunnel, you have to encrypt everything, because that's the encryption's part of the tunnel. The tunnel can't say, oh, I'm only going to encrypt some stuff. You have to encrypt everything. And the nice thing about our approach, with every single unique TCP UDP session being independent, is you can decide which ones you want to encrypt and which ones you don't want to encrypt, and which ones are already encrypted, and that makes the solution far better. So a little bit more on the security aspects of secure vector routing. So we talked about the metadata at the bottom here being encrypted with peer security policies. This encryption is based on the security association that the routers have. So even if I'm the consumer of a service, I might have different keys that I use for my tenant service routes. So the payload would be encrypted with different security keys. So even the network owner who's using the security association between the routers can't decode or see what's in the payload portions of the packets, because they use different keys. The other thing is these time-based HMAC, I talked about it before, critically important, not only to prevent replay attacks, but to ensure that no packet ever gets in on this router-to-router connection that doesn't belong in there. So a little bit about what's in that metadata. So we talked about the source of a communication being allowed to talk to the destination being a vector. And it's a secure vector in the sense that nobody else can use, like if this route is defined for a particular security camera to talk to a particular recording location that's in the cloud, no other device at that premise except the security camera can actually use this route. And we identify the tenant with many different ways that you're all familiar with. It could be any one of these above things. It could be a source address prefix. It could be a VLAN tag. It could be an interface. It could be a combination of all of the above. And it could even be a scenario where the source tells us what it is through some scheme. We've done some work with Aruba at the Air Force where they have a clear path or clear pass identity that it helps us place individual network elements into tenants automatically so that there's no configuration required. It's all automatic. And then we have this service identification. And services are sometimes, you think of them as /32 routes, sometimes they're all the way down to one and only one specific server with a known IP address. Other times, they're the names of things that we know, like Zoom. And Zoom is a good example because Zoom uses, they have like 300 CIDR block ranges for their services. They use, inside the Zoom service, they use many different protocols, from XMPP to, they actually use logging. They have logging services. They have HTTPS. They use many of as many as 15 different services are used, or different kinds of IP TCP sessions are used to create this one thing we call Zoom. So we have the ability to understand all of what Zoom does and put it in a JSON file and make it available. And we wind up understanding it as Zoom. All of those things become Zoom. Easy to you to understand. I want my employees to, on VLAN 4, which I'm going to call engineering, to have access to Zoom. Done. Same thing with Office 365. Oh, I want these people to have access, and I want these people not to have access. We also identify services automatically by looking at things like the SNI field in the if you know what that is, it's just a way of automatically recognizing stuff by scraping common names out of certificates. We don't decrypt anything. We're not a layer 7 application router, but we can figure stuff out by looking at what's on the wire, and that's what we do. And we do the best that we can to understand things that we don't know what they are, and we give you those analytics and insights. And we do everything you can do without decrypting the packet. So a couple of things that, zero-touch provisioning is really one of the hardest things that SD-WANs have to do, but it's one of the most important things in terms of making things easy to operate and move. Like you want to, if you're mobile and you need to move a whole set of operations from point A to point B, being able to just plug stuff in and have it self-configure and operate is really important. So with zero-touch capabilities, obviously there's the need to have configurations that exist and places to call home to get your configurations, your routes, your information. And you need to be able to do the lifecycle management of the software remotely and easily from a single place. These are the kind of capabilities that every SD-WAN solution needs to have, and they all do. Routers, particularly branch routers, can be hard to zero-touch provision in certain cases. Sometimes they need to have a BGP stack up and running to even talk to the network. So how do you zero-touch provision yourself when you need to have some configuration? Sometimes routers that support PPPoE need passwords and identities to connect to a network. And so how do you zero-touch provision that? So there are some special cases where we've created like QR codes to help facilitate that. But those are difficult situations. One of the things that really helps a lot if you want to make these networks awesome and easy to run and easy to provision is to have another way of talking to that router, like an LTE connection. And a lot of operators don't mind having LTE connections as long as they're not used much because they have to pay for the bandwidth. But it also provides a great backup if something goes down, or a great way to reach into the network to help manage it. So almost all of our solutions that we sell today, people opt in to get some sort of LTE communication path that they can use, so that if they have these chicken and egg problems with getting their routers configured, they can be automated. So another thing everybody needs, and every solution has, is a lot of templating. You would go crazy if you had to create snowflakes, if every router had a snowflake-like configuration. And I'll tell you a story. We did a large pharmacy chain. And what they did was, for security reasons, and this is kind of stuff that maybe exists in some of your network operations, they had every store have the same exact IP address for the same exact thing universally through as many as 10,000 locations. And so the first cash register always had the same address. The second cash register always had the same address. The first security camera had the same address. And they put them in the same VLANs, and the store switch configurations were identical. So everything was, every store was, if you saw a packet on the wire, by IP address, you could tell what the device was at the store. Then what they did is they did a specific NAT. This is where the snowflake came in. They had to have specific NAT rules on every router to get it to get the address space to work, so they could talk to the data center. And so they had to do replace the big portion of the IP of the layer of the IPv4 address with the store, what represented the address of the store. And so that's how they were able to get it to work. And every store then had a unique set of translations, and 10,000 of them. And it makes it, and they made it work. And I'll tell you, God bless them, that was a lot of work. When they put in our solution, they didn't have to do that anymore. They didn't have to do that anymore. So let's move on to this is probably obvious, but there's so many different APIs that everyone needs to use and have to make everything talk to everything. I'm sure many of these folks are here at this conference. I mean, everyone wants to share information and get information. And so these routers have to have these kinds of APIs for provisioning, for DevOps, and for third-party network management systems, and of course, third-party analytics. Now, down to the single pane of glass and network control. I mean, SD-WAN solutions, most of them today follow the lines of traditional networking, where you build your CIDR block ranges and you build an anywhere-to-anywhere network, and then you start to recognize applications, and then you apply QoS rules based on recognized applications. And it's very similar to what you would do in traditional networking. When you start routing TCP and UDP sessions and know what they are, you actually have a much better set of controls than you would have otherwise. This is a classic network management or single pane of glass showing a bunch of routers that you're looking at and managing, located on a map, and gives you current status of how things are. And you need, obviously, roles-based access controls to make sure that the right people have access to the right things, and I think that's essential. One of the things that people like about our product, and so because we're TCP and UDP session aware, we're gathering all kinds of information that routers don't typically gather, and I'll be specific. So TCP retransmissions. Now, a router can maybe pick up if it's dropping a packet, it knows it's dropping it. But if someone else is dropping the packet, and there's a retransmission request, Routers wouldn't normally know that. In fact, it's pretty hard to figure out what is a retransmission. You actually have to look at the sequence numbers in the TCP protocol and do some analysis to say, gee, is this a retransmission? And so we count that. We measure TCP retransmissions. Another thing that performance application monitoring people really want to know is they call it time to first byte, but in a TLS connection, there's, I think it's 5 back and forth packets before you get the security association established, and then you actually send your first byte of data. They call that time to first byte, and we measure that. We know that number. And it really is fascinating to know how long is it taking for a person to get connected end-to-end, security association established. These are things that our router measures on every single TCP UDP session. And we aggregate them. We have a time series database on the router itself. And the reason why we do that is interesting, because a lot of people gather session records on their routing devices, IPFix or whatever, and then they try to centralize and gather them up and centralize them. It's a lot of data. I mean, sometimes it's as much data as you're routing to get all these IPFix records. And then these IPFix records are flows, they're not sessions, and so you have to then put both parts together. And then if you want to, they all have their own start and end time, and if you want to really figure out what was going on at any one specific time, you have to wait for all these sessions to end, or you have to wait for interim reports that come out every so often. And to get a really good view of what's going on is actually rather difficult. What we do is we sample the wire every second, and we calculate summary statistics for all these services and put them in a time series database right on the router. So now the router's holding weeks and weeks and weeks of very, very detailed data about all your services, and you can pick and choose what you want to care about. And in the case of the pharmacy chain that I was discussing, they had like 15 or 20 things that they care about. That's it. I mean, they don't care about Facebook or all the other nonsense that the employees use or the guest Wi-Fi. They care about their services that run their pharmacy, and they want information on that. So they use the monitoring agent, which runs on the router, and it uses APIs to gather the data that is already there and present, and forwards it to one of these kinds of application performance monitoring devices, such as Elk Stack, or which in the case of this particular customer, they use a Kafka engine to receive all this data, and they produce all kinds of great information about their services and applications. They can tell you, for filling a prescription, they use a specific application. They can tell you the jitter, latency, packet loss, number of sessions, not just at a single store, but across their entire network. So a lot of really good information here. One of the things that, I would imagine everybody does this, but is being able to intelligently capture packets to help you debug your network or figure out what's going on when you can't figure it out. Having that ability to do that easily and quickly anywhere in your network and receive the PCAP files for analysis, really important. So that's essential. And you need a lot of analytics. I'm not going to go through all of these, but you guys probably would expect this on any modern product. This is just a software product too, so I should mention that it isn't just, it runs on any white box hardware. It also runs in any cloud. It runs in AWS. It runs in Azure. And it's the same exact code, same exact software version, same exact binary image. It runs in Alibaba. It can run anywhere, and has moderately high. It has much higher performance than any of our competitors that use IPsec tunnels, essentially achieving 4x the performance on the same hardware because we're not encapsulating and decapsulating. And I will speak a little to how inefficient tunnels are in terms of encapsulating and decapsulating at a software engineering level. I'm an engineer. I'm not a businessman or a marketing guy, but when you encapsulate packets, you have to essentially do a mem copy to move the whole packet down to make room for the new header. Then you have to create the new header. Then you have to walk the packet to do the checksum. And you have to do the exact reverse when it gets to the other side and you take the tunnel header out. That's really inefficient stuff. And by the way, on a 10 gig interface, you might need to do 30 million packets a second. And that's a lot of mem copies. It just uses up a lot. Moving packets or moving bytes is what's using up all the time. And it actually adds latency. I don't have the slide here, but we sold to our solution to someone that was using Cisco's DMVPN, which is, I forget what router they were doing it on, but it was a lower end router. And they put our solution in, and the latency in the network was cut in half. And we didn't expect that, because we figured Cisco's using ASICs or something. I mean, it must be, but it was cut in half, and they were very, very surprised. And they also saw far fewer lost drop packets. I have the slide on my computer, but I don't have it in this presentation. And it came from the customer. They just came out of their measurements on their own. We didn't prompt it. It was really quite astounding. Obviously, tracking WAN events, super, super important. And I wished I had put a slide in here on, before I get to the use cases, on the power of AI in terms of helping run your networks. And I am even though I'm a CTO and I'm supposed to know about technology and everything, I'm actually a dummy when it comes to things I don't know about. And I didn't know about AI. In fact, I was dubious about it. I figured it was, because it's such a trendy thing, everyone's talking AI, and I really didn't get it. And when Juniper acquired our company, I started to talk to the AI data science team who wanted to understand our product. And they told me stuff that astounded me. So I'll give you an example. So the Mist AI solution is really quite good. And what they told me was their number one problem. And what they do is they focus on operational problems in terms of what they turn their data scientists on. And their business is selling access points. And they would go in to an existing facility where they had access points made by a previous vendor, and they would pop them off and put the new access points on. And that was their business, selling access points. Well, invariably, those wires up in the ceilings occasionally had issues. The wiring sometimes had a bad crimp, and they always worked. But sometimes they didn't work great. And what happens with trouble tickets where people say, I'm not getting the throughput I want, or it's not working well, the cable's the last thing that you turn to prove out is not correct. And usually, it's a lot of effort to convince a customer that it's a cabling problem to begin with. And meanwhile, cabling problems happen all the time. So what they did was they started tracking the real data from network devices when there was identified bad cable by using and they actually collected hundreds and hundreds of known bad cables. And they started building data models around it. And they looked at things like giants or runts or framing, any kind of evidence of a framing error or evidence of a speed renegotiation. And they put their data scientists on it, and they cracked the code. And now they can tell you when a cable is going bad. And the great thing for them is, and for the people that use this solution, is that you don't have to convince the end customer now, because it's backed by all this science. It's like, yeah, this cable's probably causing your problem. And it's astoundingly awesome. And I was like, whoa. And then they showed me some of the other things they're doing with artificial intelligence. And we're taking our data that we're collecting in our secure session router, our session data, our TCP retransmissions, our time to first byte data, and we're putting that into their models. And their models are really fascinating. They're trying to figure out how to best measure the experience users have on a network they call it client to cloud. And we're doing that, and I'll have to tell you, it opened my eyes about what AI can do. I sat through a presentation here this morning on AI that was really quite interesting, but I have to tell you, think about anything that you do or your people do operationally over and over. The complaint comes in, what's the flow chart to solve it? Ask these questions, get these traces, do this, do that. The computers can do that. These computers can get can get traces automatically. They can analyze them. They do whatever a human does. If you just watch humans and how they've solved problems, you can solve those problems automatically. You can. And boy, that's the future of networking. I'm a believer in that. I can't tell you how many days I've spent pouring through traces. I don't know how many of you have done a lot of that, or how hard it is to find problems. And when you find them, you pat yourself on the back, and then it happens again. Another new problem, another new problem. At the missed Wi-Fi, they had so many problems with people complaining my device couldn't connect that they started to automatically gather PCAP traces every time a device couldn't connect and process it automatically to figure out why isn't it connecting. And it's phenomenal. Pay attention to this stuff. It's going to change the operational aspects of running networks. So on the customer use case here, we have one with the DoD, and there's some folks here from my team if you have questions about it, because I'm going to probably know about 50% of it. The challenge was empowering the servicemen to, basically it was about getting to the cloud, really, and it was our partners, Microsoft, in the solution. And as part of the solution, we're routing sessions and not packets. And this is up and running, and Boris, how many bases are we at?
We're at 3 Air Force bases, 1 Army base,
Okay. Okay. So Boris's answer was we were at 3 Air Force bases, 1 Army base, and some other stuff. But this is deployed. This is live. It's interesting. If people are observing it, seeing it in action, seeing what the benefits are. They're using our end-to-end micro segmentation and zero trust policies. And the results are, we think the results are promising. I think we're hearing good things back about it. So this isn't just a technical story. This is real, and we're very excited about it. I did want to save some time. I have one more use case. I did want to save some time for questions. Well, I think this is a more specific example of the Air Force deployment, and that we have. We're actually. If there's any questions about this, we can answer it. But we are at the meet me point. We're also have connections to these other networks. And by the way, we do everything that routers do. We do BGP, we do OSPF, we do, we do everything that you would need with your routers normally. A lot of times, people want those things because they don't understand that they can actually use these new ways of routing to avoid those things. But we do support them all. In fact, they're doing a lot of BGP work at the Air Force. And that's the end of my presentation. I did want to leave time for questions and potentially and I'm willing to answer things on any topic. So does anybody have a question? Sorry? Yep. I'm sorry, I didn't hear you. Yeah. Is the 128 that is a router itself?
Is it 128-bit encryption, or what is that 128 on your slide?
Oh, okay. That's probably an error on my part because our company name before we were acquired was 128 Technology. Yeah. That's really like a company indicates that's our software. It should say SSR because it's now Juniper's SSR. So I apologize for the confusion. That's a very good question.
I noticed you say you're on Air Force bases and Army base. How are you passing on the secure data? Is there only KG-175 things like that?
The question was, how are we passing the secure data at the Air Force? Do you have an answer, Boris? Do you want to use the? Yeah.
Yeah, so we just transport, so any data that's secure would just go through us just like any other router. We do have an architecture that we've been deploying with the DoD, especially with the Air Force as part of ABMS that we call Session Smart Routing for Classified, which is an architecture that allows us to essentially do SD-WAN in classified environments using cryptos to pass DSCP traffic. But we could sit on the SIPR side, we could sit on the NIPR side, we could enable SD-WAN on both classified and unclassified side. We have ATOs for both. But in this instance, for what we're doing for the ITAS and the NAS program, we're specifically sitting on the NIPR side. So we're providing the kind of the session smart routing, secure vector routing capabilities of sending data efficiently into the cloud and into the other DoD networks like the DISN and AFNet. So because we have the capability to work as both the overlay and the underlay, since we are, first and foremost a router that just happens to do SD-WAN really well, it allows us in that top layer to connect into the APCs, to connect to the DISN, to the AFNet, and the other networks using BGP and OSPF, so standards-based protocols. And then on the bottom part where we're doing the modernized networks, it allows us to efficiently connect bases through meet-me points into clouds and other locations without having to worry about creating a spaghetti soup of tunnels. So I kind of like to explain it as the simplicity or the power of SD-WAN with the simplicity of traditional hop-by-hop routing, where every router can make an intelligent routing decision based on zero trust policy. Any other questions? We got 8 minutes worth of questions, so. Yes, sir. Yeah, that's a great question. So the real power and from a tactical perspective, one of the challenges that warfighters are seeing is that a lot of the tactical networks or tactical kits that are deployed today are single-stranded from a WAN perspective. So they either have, like a SATCOM link, right? And then if that SATCOM link goes down, then they've lost connectivity. Well, we're starting to see a lot more of, especially in the new exercises like the Guide 3 that just happened in Michigan and the ABMS exercises, is how do you leverage multiple forms of connectivity to ensure resilience all the way at the tactical edge? And that connectivity could be everything from, MIL-SATCOM to the new, LEO constellations like Starlink to, LTE and 5G. And how do you seamlessly leverage all of these different network paths so no matter what happens to a specific network, you still have connectivity? And that's exactly where this capability adds tremendous value. So if you the analogy I like to use is if you think about kind of what VMware has done from a server virtualization perspective, where they've created this abstraction layer between the applications and the physical hardware that those applications run on. And as long as you have enough hardware redundancy, if a hard drive crashes or if a server reboots, the apps continue to work. They have no concept of what's happening in that underlying network, that underlying hardware layer. What we're doing with secure vector routing is we're creating that same sort of abstraction layer between the apps running across the network and the physical network paths. So once again, as long as you have enough network paths, we could change what path the traffic goes through. So if you're in the middle of a phone call, or if you're watching an ISR video, or if you're doing some sort of application across the network and one of your paths gets denied or jammed, we could in real time revector that traffic through different paths without dropping that session, without breaking that connection. So as a warfighter at the edge, your voice continues to function, your video continues to function, your apps continue to function, regardless of what's happening in the network.
Just so you know how that works, if we need to move a session from one transport to another, all we have to do is put metadata in the very next packet. And because it has that universal session identifier, that unique ID, when it travels on the new pathway and gets to the destination router, it says, oh, this is on a new pathway, and it heals the return path. So it's like topology independent fast rerouting down to a session by session basis. And you can move the voice when the SLA for voice is no good and leave the HTTPS traffic alone. So it's very, very flexible and very fast. It's instantaneous. Just the very next packet can go on the new pathway. So I just wanted to mention that.
And this is in contrast to kind of what happens today, especially with legacy tunnel-based SD-WAN solutions, because in that same scenario, if something happens to a primary path and you're going through a tunnel, what happens is the tunnel goes down, all of the sessions in that tunnel go down. So if you're in the middle of a call or if you're watching a video, that connection is severed. A new tunnel has to be reestablished over a backup path, and then all of the sessions have to be reestablished again. So as a warfighter, you've lost connectivity for some period of time while that network kind of self-forms, self-heals itself. With secure vector routing, all of that's avoided since we maintain that end-to-end session state. And without tunnels, all of that revectoring happens automatically on the fly, kind of like Waze navigation for the network. Sorry, what was that? Happening automatically, correct. So once again, as the end user, you have no concept that this is happening. It's completely seamless, just like with VMware. If a hard drive crashes, server reboots, it just works. The apps just work. The question was, do we see any challenges with different WAN technologies? No, so this works extremely well across different WAN technologies. So we've deployed this operationally across, everything from LTE to Starlink to MilSatcom to, and from a bandwidth perspective, from everything as low as 3 kilobits per second to 100 gig routing, which is what we're doing at the Air Force. So the solution scales extremely well across different sorts of WAN connections and different WAN characteristics and bandwidth rates. Not at all. And in fact, what we've done, like most recently for the Guide 3 exercise, Global Information Dominance exercise, we worked with Paycom. They have their CFK kits today, which are CSFC certified, but their challenge is, once again, they're single-stranded, right? They have a single SATCOM link or just a single path out. What we were able to do is front-end their existing certified solution with our Session Smart Router and suddenly allow them to participate across multiple WAN paths. So the beauty of that is, from an accreditation perspective, their solution is still CSFC certified, it's accredited, but by front-ending their existing solution with the SSR, we've now breathed new life into that capability. So very rapidly, we were able to take kind of existing tactical kits and modernize it with, tunnel-free, secure vector routing, SD-WAN. And as part of that demo, we were, leveraging Starlink, LTE, and MPLS between Michigan, Hickam Air Force Base, and Nellis Air Force Base, and we were able to do voice, video, and data, and seamlessly reroute traffic, unplug, different network paths without dropping that connectivity. So whether it's CSFC or whether it's Type 1, doesn't matter. So it doesn't matter if it's CONUS or OCONUS. I mean, in fact, one of the other kind of interesting capabilities, we're working with Joint Chiefs of Staff, and from an OCONUS perspective, one of the interesting things that we can do by not using tunnels is obfuscate the data across the WAN. So one of the things that Patrick talked about is between the Session Smart routers, we're using completely randomized ephemeral ports with completely different crypto keys. So as an end user, one of the challenges was if you're deployed somewhere OCONUS, you're working out of a hotel room, the challenge with a tunnel-based solution is if you're a bad actor sniffing that hotel WAN traffic, with a tunnel-based approach, you see this giant IPsec tunnel, you know exactly who the source and destination are, and if you're state-sponsored, you could capture that traffic and eventually break into it. The beauty of this solution and why JCS deploys it is that every single session uses completely randomized ports, completely different crypto keys, and the data gets obfuscated or it blends with all the other random noise traffic across the network. So it allows that data to not be, just encrypted from a ComSec perspective, but obfuscated from a transec perspective. So whether it's CONUS, OCONUS, really doesn't matter. Does that kind of answer your question? Sorry, what was that? No, so another architecture we have is we could use a relay router, and we demonstrated this when we were out in Germany for on-ramp 4 back in February with the ABMS program. What we did is we ran a relay router in AWS GovCloud for that instance, and so we had simulated end users at Ramstein Air Force Base going through our relay router in the cloud, connecting to the launch tool teleport facility, so connecting back to DISA. By using the relay router, that relay router obfuscated the connectivity between the edge to the teleport site. So if you were someone sniffing traffic in the middle, you had no idea who we were talking to. We were obfuscating that end-to-end connection by leveraging that relay router. And so another interesting architecture we have is, a common threat these days is Bgp hijacking, where, a nation state or a bad actor could inject Bgp routes and pick up your traffic as it's going end to end. And so we could do things like detect that traffic and instantly spin up a new relay router and redirect the traffic completely. So traffic that was originally going, one path, we detect some anomaly, some sort of security event, either through our capability or through our API partners, and we could revector that traffic through a completely different router anywhere else in the world. And because the solution is 100% software based, we could spin up that router in any cloud, anywhere, anytime.